yesterday we talked about remainder factor theorem. Today we're going to use that more frequently. We can check to see if x minus 5 is a factor by seeing if it divides this polynomial. We can also do that with synthetic division and do it a lot quicker. 1, 0, negative 24, 4, negative 5, and 2. And if I set up my synthetic division, I have 5 times 5 is 25. 25, oh sorry, that would be a 1. 1 times 5 is 5. 25, that'd be 1. 1 times 5 is 5. This would be 9. 45, 40, and 200, and 202. Now, clearly that doesn't work. But if I check and confirm, if x minus 5 was a factor, that would mean that 5 would have to solve the equation if it was set equal to 0. Which means that if I plugged it in, I should get 0. Well, if I plug 5 in, I would expect not to get 0 because I did not get a remainder 0. But if I plug 5 in, I get 5 to the 5th, which is absolutely huge. 5 to the 5th minus 24x cubed. Let's do it in a calculator. So plug it in, and I get 202. Incredible. What we should notice is that these are the same thing. That my function value equaled my remainder. And this is the remainder theorem. If you have a polynomial of a positive degree, then for any number that you want to plug in, basically P of C is the remainder.
So if you had to rotate this region around the y-axis, you'd have to...
I take a polynomial that's equal to a quotient times some x minus c plus p of c. So another way of doing this is if I say I take p of x and divide it by x minus c, I'm going to get a quotient q of x plus this remainder over my divisor. Now look at what this makes easier. If I want to find p of negative 5, before I would have to plug negative 5 into each of these. Now all I have to do is synthetically divide with negative 5. 1, 2, negative 1, and 4. Do my multiply, add, and multiply, and add. And I get negative 66. And this means that p of negative 5 is negative 66. This actually has a different name. This is called synthetic substitution. And it is extremely powerful for plugging in numbers into long polynomials by hand and getting their function values really, really quick. Wasn't that quicker? If the remainder was 0, what does that mean? Now this remainder was not 0, but if I do have a remainder 0, we know something even more. Look at the factor theorem. If we have x minus r as a factor, that means that r is a root. And there's a root of the equation set equal to 0. This is not only a way to check if a number is a root, you can also check for factors. So, lots of questions we can ask. Is x minus 2 a factor? If that would be true, then 2, that also means that 2 is a root. In fact, saying x minus 2 is a factor and saying 2 is a root are equivalent statements. So I'm going to synthetically divide with 2 and see if I get a remainder 0. Same thing as if you were to plug 2 in, but this is a lot faster. So I set up my coefficients. 1 times 2, negative 2, negative 4, 1, 2, 6, 12, and a remainder 0. Don't worry about going any further. The answer to the question is yes, and we've just shown it. Then if I want to say if x minus 2 is a factor of this, I get 2, 1, negative 5, negative 38, 132, and 360. Bring it down, 1, negative 3, negative 6, negative 44, negative 88. Add that, we get 44, 88, and a big fat no. No remainder 0. This can also help solve equations. If I know that 1/3 is a root, I can use that to factor. Watch this. 1/3 is a root, that means x minus 1/3
Yeah, I think you'll have to use it one time.
is a factor. So I pull this out, 3, negative 1, negative 27, positive 9.
Because it's
and I get 3 times 1/3 is 1, 0,
the ends to x's.
0, negative 27, negative 9, and 0. And what I'm left with is this 3x squared minus 27. Well, that can factor into this. And if I set that equal to 0, that means my other roots are plus or minus 3. And so my total solution would be the 1/3 originally and the plus or minus 3. If I know negative 4 is a root of this one, I can pull the x plus 4 out. I can factor or divide x plus 4 out very quickly. 1, 9, 16, negative 36, negative 80. So I got negative 4, 5, negative 20, negative 4, positive 16, negative 20, positive 80. And then I get x cubed plus 5x squared minus 4x minus 20. And if I set that equal to 0 and factor by grouping, pull out an x squared, get x plus 5, pull out a negative 4, get x plus 5. Greatest common factor is an x plus 5, and I have x squared minus 4. I know from this my other root would be a negative 5, and here would be a plus or minus 2. So all of my solutions grouped together should be negative 5, negative 4, and positive and negative 2. In number 6, 2 roots are given. So let's pull one of them out. I'm going to go, we'll pull the 4 out. 1, 2, negative 51, negative 32, and 560. Multiply, add, multiply, add. 27 times 4 is 108, negative 108, so negative 140 and positive, or negative 560. Then I'm going to take these same coefficients we just have right here and now synthetically divide with the 5. I'm going to pull the 5 out of what's left. 11, 55, 28, and positive 140, and 0. And what I'm left with is this x squared plus 11x plus 28, which very easily factors. And so I know that all 4 of my roots would be negative 7, negative 4, positive 4, and positive 5. The last neat question we can ask is how many times is 6 a root of this thing? 1, negative 17, 70, 252, negative 2376, and 4320. So if I go multiply, add, multiply, add, multiply, add, I'm going to cheat. Multiply, this would be negative 720, and then multiply 4320 negative. So I know it's at least once. Let's do it again with 6. Get negative 20, negative 16, negative 96. That would be 180, 720. So I know it's at least twice. Let's keep going until I don't get a remainder 0. 1, 6, 1, 6, negative 10, negative 60. Done. So it was twice, which means that 6 is a double root.